In some previous section, we divided the class of ordinary differential equations into two types, linear and nonlinear. We now consider briefly another kind of classification of ordinary differential equations, a classification that is of particular importance in the qualitative investigation of differential equations. Recall that a first-order ordinary differential equation has the following general form, or the normal form: y prime equals some function f of x and y. Here x is the independent variable and y is the dependent variable. If f in the first equation does not explicitly depend on the independent variable x, or x does not appear in the right hand side of the last equation, then it takes the following normal form: y prime equals f of y only. Equation 1 is called a first order autonomous ordinary differential equation in y. We shall assume that f and its first derivative, f prime, are both continuous functions of y on some interval I. Let's have a look at some examples. The following are some autonomous first-order ordinary differential equation or first-order initial value problems. Y prime equals 2y times 1 minus y. Notice the right-hand side of this equation depends only on y, not on the independent variable. Similarly, in example 2, p prime equals k times p. Here k is some constant and p is some dependent variable. An independent variable, possibly t, with some initial condition. So this is another example of a first-order autonomous ordinary differential equation. Similarly, in examples 3 and 4, we see the right-hand sides of these equations depend on the dependent variable, not explicitly on the independent variable. Consider g is some function of x defined by this polynomial, x squared minus 5x plus 6. And we have the value of the function g at 2 equals 0. Then the number 2 is called a zero of the function g. Similarly, 3 is another zero of the function g. The zeros of the function h, defined by sine of x, are the integral multiples of pi, since sine of n pi equals 0 for all integer n. Now consider the first order autonomous differential equation as shown in equation 1. The zeros of the function f in equation 1 are of spatial importance. We say that a real number c is a critical point of f if c is a zero of f. That is, f of c equals 0. A critical point is also called an equilibrium point. Now we observe that if we substitute the constant function into the equation 1, then the both sides of the equation are 0. If you differentiate y of x with respect to x, you get 0. And in the right hand side, we get f of c, which is also equal to 0 by the definition of the critical point. This means that equation 2 here is a constant solution of the equation 1. For example, the functions y of x equals 0 and y of x equals 1 are two constant solutions of the following autonomous ODE. A constant solution y of x equal c of equation 1 is called an equilibrium solution. Equilibria are the only constant solutions of an autonomous ordinary differential equation. Consider the autonomous ordinary differential equation. Y prime equals 2y times 1 minus y. The critical points of this equation are 0 and 1. Since the right-hand side of this equation becomes 0 at 0 and at 1. Now we subdivide the whole real number line, the negative infinity to positive infinity, into 3 subintervals. From negative infinity to 0, and from 0 to 1, and from 1 to positive infinity. Let's take some test values from these intervals. In the first subinterval, the negative infinity to 0, we take negative 1 and we investigate the sign of the function f. If we substitute negative 1 into the function f, we obtain something negative. 2 times negative 1 times positive 2, which is negative. So the sign of the function f is negative. This means that y prime on this interval, negative infinity to 0, is negative. And this means from calculus that y of x must be decreasing function. And this is indicated by this arrow. Similarly, if we take another test value, for example 1/2 from the subinterval 0 to 1, if we investigate the sign of the function f, we obtain it is positive. And this means the solution y must be increasing. And lastly, for the subinterval 1 to infinity, we take the test value 2 and the sign of f becomes negative, and this shows the solution y must be decreasing. Now, if we put the real number line vertically as y-axis, and if we show the subintervals here, now we put the arrows, the down arrow or the up arrow, according to whether the solution is increasing or decreasing, we obtained this figure. For example, in the interval negative infinity to 0, the solution was decreasing. So we put a down arrow. And in the second interval, 0 to 1, the solution was increasing. So we put an up arrow. Similarly, in the last interval, the solution was decreasing. So we put a down arrow. This vertical line with arrows is called a phase portrait. And the vertical line itself is called the phase line. Now let's put the direction field of the autonomous differential equation side by side to the phase portrait. The constant solutions are plotted with the red dot lines. And as shown in the table, we see the direction field is behaving exactly in the same way. The solution must be decreasing in the subinterval -∞ to 0, and the solution must be increasing within the subinterval 0 to 1, and again the solution must be decreasing within the subinterval 1 to +∞. Attractors and repellers. Suppose the function y equals y of x is a non-constant solution of the autonomous ordinary differential equation y prime equals f of y, and c is a critical point of the ordinary differential equation. There are basically three types of behaviors that y of x, the solution, can exhibit near the critical point c, as shown in the following figure. When both arrowheads on either side of the dot labeled C point towards C, as in figure A, all solutions y equals y of x that start from an initial point x sub 0 comma y sub 0 sufficiently near C exhibit the asymptotic behavior. For this reason, this critical point C is said to be asymptotically stable. This type of critical point is also referred to as an attractor. When both arrowheads on either side of the dot labeled C point away from C, as in figure B, all solutions y of x that start from a critical point with coordinates x sub 0 comma y sub 0 move away from C as x increases. In this case, C is said to be unstable. An unstable critical point is also called a repeller. For obvious reasons. The critical point C, illustrated in figures C and D, the critical point C, illustrated in figures C and D, is neither an attractor nor a repeller. But since C exhibits characteristics of both an attractor and a repeller from one side and from the other side, we say that this critical point C is semi-stable. Let's consider the previous example. Y prime equals 2y times 1 minus y. The critical points of this differential equation are 0 and 1, as shown in this figure. And by the previous discussion, the critical point 0 is a repeller because the arrowheads from either side of the point 0 are in the opposite direction. And the critical point 1 is an attractor for the reason we described previously. Let's have a look at the behavior of the solution of the autonomous differential equation y prime equals 2y times 1 minus y in this applet. Let us first plot the direction field of this differential equation. And the constant solutions are shown by the red dotted lines. Here, the point 1 and the point 0 are the critical points. Let's take a point near the critical point 0. Since 0 is a repeller, we see that the solution is moving away from the constant solution y equals 0 from either side. The solutions are moving away. Now, if the initial value y sub 0 is near the other critical number or critical point 1, then since the critical point 1 is an attractor, the solution passing through this initial point is getting attracted by this critical point, and the solutions behave asymptotically from either side of the critical point 1. So 1 is an attractor and 0 is a repeller. And this is also true for any other point, not necessarily on the y-axis. If we take a point A with coordinates with its y coordinate same as the initial point y sub 0, then any solution passing through this point is moving away from the critical point, the repeller. Or if we take the point A with its y coordinate near the critical point 1, which is an attractor, the solution is getting attracted by this constant solution y of x equals 1.